Okay, so making this D gamma, D is the density. So in R, this is what we would put in. So X is the variable, and you can kind of see here it has the parameters. So alpha is the, oops, you know what? Sorry. Let me go back up here, my little notes. I'm sorry, we didn't talk about alpha yet. Right here, alpha is called the shape parameter, and we know beta is called the scale from the previous page. So sorry, shape is alpha. So in R, it says shape, and you put in the alpha number. You can see rate would be lambda, or scale would be the beta. Now, when you're putting these things in, hold on, when you're putting these things in R, you put one or the other, not both. So you choose. So we are generally going to put the scale number in. Okay, so just to get a pictorial idea, it's kind of skewed to the right, sort of like an exponential. And so why do these variables get their name, sorry, parameters get their names, is they do, it's kind of aptly named. So here I have separate gamma densities plotted where I keep the beta equal to 2 and I change the alpha number. Okay, so this, let's put it maybe down here. So the darkened one in black would be the PDF, that's what the D is, the density, for a gamma distribution with shape. I pick the lowest number, 0.5 for alpha, and scale equal to 2. Okay. And so I just dittoed all of these, I just changed the shape number. So, right here. So like this first dotted one would be alpha then equal to 1, right? So you're kind of going to see what happens when alpha increases. This next dotted one, alpha equal to 2. And the last one, alpha equal to 4. Okay? So why is alpha called the shape parameter? Well, because the shape changes. As alpha increases, the shape becomes more symmetric. Right? And if I made alpha big enough, it would actually kind of merge over and start to take on kind of actually a bell-shaped shape. Now, what happens if I make beta or change beta? So here I kept the same values of alpha, I just made beta bigger. Okay? And so same deal over here, using this function to graph it. The one in dark here would be for alpha equal to 0.5. Right, so again, as alpha gets bigger, the shape is going to change. Just label these again. So the next one, alpha is 1. Next one here, alpha is 2. And then the last one, alpha is 4. Okay. So if you look at the pictures, it doesn't look like much change, right? As alpha got bigger, the shape changed. But what's different? Right? If we look down here, what happened? This went from roughly 0 to 15. This goes from 0 to 25. So when beta gets bigger, the scale gets bigger. I can write correctly. The scale is stretched, right? So beta kind of stretches out the distribution. So that's what's called a scale parameter. As beta gets bigger. Okay, but that's generally the shape, right? Why do I care? Well, because we use these distributions to model things in the real world. Right? We looked at the exponential distribution once upon a time, which is nice and skewed to the right. What's an example of something we would model with an exponential distribution? It was always lifetimes, right? Or failures or something like this, right? And something skewed to the right, it means the probability gets less and less and less as the value gets larger, right? So the probability of something continuing to live as it gets older should get less and less and less. So it makes sense. Gamma distributions can be done kind of the same way, used similarly. So that's what it looks like. I just wanted to show you so you can actually visualize this, know what one looks like. Okay, well, thank you. Let me scooch back up. So a couple things. What does the moment generating function look like? So that's this here. Currently, we're actually not going to do much with it, but I'm just showing it to you. And yes, there's two counterparts, depending on whether you're using beta or lambda, right? But they're both equal to each other. So if I plugged in 1 over lambda into beta, simplified this, I would get this piece over here. Couple of things that are going to show up, if not in this set of notes, the next one we're going to jump to is the sum of two independent gamma random variables. If I have x and y are independent, different gamma random variables, and they have the same beta, so x and y, they have the same beta, maybe different alphas, then x plus y, kind of like with normals, I add the means, here I add the alphas. X plus y would be gamma, but I just add the alphas together. Okay, another kind of transformation, if I have x, which is a gamma distribution, and then I take some transformation like k times x, just like in a normal, if you take k times a variable, the k gets multiplied with the variance, here it gets multiplied with the beta. Okay, and last but not least, we're going to use this one most recently at the end of this notes, is this goofy looking thing. Okay, for any alpha and beta, the integral from 0 to infinity of x to the alpha minus 1 times e to the negative 1 over beta x is equal to beta to the alpha times gamma to the alpha, or gamma of alpha. Okay, sounds great. Where does that come from? It's actually a very useful identity, right? And it comes into the fact where, like I said, this integral, actually, said I was going to come back to that. This integral, let's just look at this integral real quick. You can stay put. I'm going to flip back if I can do that. Camera 1, camera 2. So here I have x to the alpha minus 1 times e to the some constant times x. It almost looks very similar to this gamma function. X alpha minus 1, e to the constant here is just a 1. Right, so if you actually try to do that integral, right, if we try to, in other words, integrate this PDF, it really boils down to an integration by parts problem, which, as we saw, if alpha is not a nice round whole number, the integration by parts is kind of difficult. So this is another identity to help us simplify this. So where is this coming from? I got away from that. Right. So hold on. Yep. No, that's the setup. So if I do integrate this thing, if I take my PDF from the previous page and I do, sorry, get that centered. If I do integrate that, so integrate from 0 to infinity of 1 over beta to the alpha, gamma alpha, times x to the alpha minus 1, times e to the 1 over beta times x, dx. Okay. This is the PDF. If I integrate the PDF, that has to be equal to 1. That is correct, right? Just by definition of it being a PDF. Now this part, although it's written in symbols, this is a constant, right? Beta and alpha is a constant. Gamma to the alpha is a constant. So you can actually bring this to the outside. Okay, bring the constant to the outside. And since it's a constant, I can multiply both sides by that. So if I multiply this side by beta to the alpha times gamma to the alpha, then I multiply this side by the same thing. Whatever you do to one side of an equation, you do to the other. So this piece here cancels with that piece there. And then what am I left with? The integral, just to clean it up from 0 to infinity, of just the inside piece is left on the left-hand side. X to the alpha minus 1 times e to the negative 1 over beta x is equal to beta to the alpha gamma alpha times 1 is just beta to the alpha gamma to the alpha. It's really not a rule or a property, just sort of a reworking from a definition. Okay. Now I did put a star up there. Well, I'll put a double star. This will be important. We actually use this in your homework, and we're going to see how in just a little bit. Okay, so thank you for bearing with me through that. So let's take a look at how we're going to make use of some of those. All right. So I'm sorry, this is actually one more property that's going to come into the part 2 notes that we're going to get into in a little bit. So let me touch on this before I get to the examples. Actually, no, we don't need that quite yet. Let me come back to that in the end. We'll go ahead and jump down here. All right, so example 3. For x, having PDF, looks like 1 over 128 times x squared e to the negative x over 4. I want to find the expected value of x, the variance of x, and the expected value of x cubed. Okay? So there's 2 ways to go about this. I could jump right into my expected value of x is taking the integral of this thing of x times the PDF and try to do the integral. Or, big hints, we know about this gamma distribution. Right? If I can recognize this as a gamma distribution, so let's take a look. So let's see. Now the 1 over 28, it's a little weird, but this should hopefully be ringing bells. So I'm gonna leave myself a little bit of space. So if I say, okay, x to the 2, that's kind of like x to the 3 minus 1. That's x to the alpha minus 1 times e negative x over 4 is the same thing as negative 1/4 x. Right? So I have x to the alpha minus 1, e to the 1 over beta times x. That's should be ringing bells. This is setting up as a gamma distribution. The only thing is, does this number work out? So let me check that. So if this was a gamma distribution, again, what am I talking about? We flip back 1 page. I'm looking at this PDF here, right? The constant in front should be 1 over beta to the alpha times gamma to the alpha, or gamma of alpha. I keep saying that wrong. So my beta, if it were, would be 4. My alpha would be cubed, 3. Can't say anything right today. And gamma of alpha, gamma of 3. Now, I'm sorry, I said this was equal. I'm actually checking this with a bit of a question mark there. 4 cubed is 64. What's gamma of 3? Gamma of a whole number is that number minus 1 factorial. So this is actually 2 factorial, right? So 64 times 2 is 128. So all I did is I confirmed, okay, this is really what? This is a gamma distribution with alpha equal to 3, beta equal to 4. Is that okay? All right, so for part A, how does that help me?
Well, you got alpha and beta, and you can apply the gamma distribution just like that.
Exactly. So this little bit of work saved us a bunch of work down here. So what is expected value of x is what? Alpha times beta? So right away, alpha, 3 times 4. All right, so our expected value is 12. What's the variance? Look back a page, alpha times beta squared. So 3 times 4 squared. 48. There we go. 3 times 16. Hey. Ah, done. That was nice.
This is going to be
Okay.
more complicated, I think, because I think we have to use the moment generating function, maybe?
You could. I'm not going to do it that way. I'm going to try and show a simpler way. Yes, you possibly could.
Because we need to do something like this, like it's the 4th.
But let me pause for a second. So in the homework, while we're touching on that, in the homework, I'm asking an inverted problem. I'm giving you the value and asking you to find alpha and beta. We'll touch on that in a little bit, all right? But it's kind of similar. Actually, no, we're going to look at one in the next section. I keep get things straight in my head. All right, let's look at this. Expected value of x cubed. Yes, there are potentially different ways to do this. You could bring in the moment generating function. Right, you take the third derivative and plug 0 in for that. But let's see a different way, all right? And yes, this is going to be part and parcel of something you're going to do in the homework problem. And that's why, when I mentioned I pushed the homework back till tomorrow, mainly because of this, what we're about to do right now.
Found the problem.
So- So let me set this up. So how would I set this up normally? I would say, okay, I'm going to integrate from 0 to infinity. I take whatever's inside the expected value, x cubed.
Hold on.
Hold on. And then I multiply it, sorry, with the PDF, right? So 1 over 128. So yes, I recognize it like this. I'll just go ahead and write it in its simplified form. 1 over 28 x squared times e to the minus 1/4 x, right, dx. So based on the definition of what expected value of x cubed would be, that's what I would want to find. Okay, not too bad. So I will go ahead and combine these two, simplify it. So I have the integral from 0 to infinity. Let me see. I kill two birds with one stone. I'm going to bring the constant on the outside. So sorry. Scooch that. They bring the constant on the outside. And so I would have x cubed, x squared gives us x to the 5th, and e to the negative 1/4 x dx.
That's just another gamma distribution.
Roundabout. We're going to get there. So let me pause, let people get caught up. Okay, so far I didn't do anything other than I brought the constant out and I have this. But yeah, this is the relationship between a gamma distribution. Because I have a gamma distribution. In a gamma distribution, I have x to some power. If I'm finding the expected value of x to a power, all I do is really change this power right here. Okay, so I could think of this as the setup of a gamma distribution. Instead of a 5, sorry. Think of 5 as a 6 minus 1. Okay. We have x to the power minus 1 times e to the negative 1 over a number times x. So here's this identity that we just took a look at a little bit ago. If I take the integral now of x to some alpha minus 1 times e to the negative 1 over beta times x, we simplified and derived this as what, the beta to the alpha times the gamma of alpha. Now I know we started with one type of gamma distribution, and here we changed the numbers, but it's okay. I can apply this as long as I have the appropriate numbers in here. So according to this, that says that this entire integral is equal to what? This would be the beta, would be 4. Right. My 5 can be written as 6 minus 1, so the alpha is 6. So it would be beta to the alpha, 4 to the 6, and then times gamma of alpha, gamma of 6. Then I'm going to drop my constant, that's 1 over 128. Okay. Let me pause because it's an important part. Does this make sense what we just did? That's like the key to the problem there, right? So the constant could have stayed inside, it just makes it a little bit clearer. So I just use this identity. Now I just multiply across. 1 over 28 times 4 to the 6 times what's gamma of 6?
I think I figured out a general
5 factorial,
right?
which is 120. But anyway, plug all that in, 3,840. Okay, get that. Okay, so that completes this part. Any questions? All right, so let me take a quick break. Let me pop over and take a look. So before I'm going to roll into that part 2 set because the two are merged, or linked. Here. Oh, I never even. Sorry. Never even logged in to start.
Figuring out a formula for this. That is huge. Oh, that is huge. X the N for gamma distribution.
4, here we go. Okay, so as it relates to this gamma stuff, so this is stuff we did the other day. Hopefully this looks kind of familiar. So these 3 problems. So using our gamma function. And then here we are with stuff we kind of just did. So for 7, part A, you're told that X has a gamma distribution with a mean of 10 and a variance of 20. So you know what that's equal to, and I want you to find the parameters of alpha and beta, right? And so, right, clues.
I saw C and was scared.
Right, and so clues, hold on. So clues, right, we can set these 2 individual equations up in terms of alpha beta and alpha beta squared and try to solve for one variable or the other, or one parameter or the other. Okay? So we didn't do it like that in class. I think we can, wrong button. I think we can do it. And then, all right, write the PDF of X once you find alpha and beta. So that should be pretty straightforward. And then this one, all right? So part C. Okay, part C. So I have the expected value of what? 3 times X, and then minus 5X to the 4th. Okay? So my clue is here, remember, expected values can be broken up over sums and differences. All right, so this is really 2 expected value problems in 1. This would be the expected value of 3X minus the expected value of 5X to the 4th. Right, and constants can come to the outside. So we just did, hold on, we just did expected value of X cubed in a gamma distribution. Right, now I'm asking you to do expected value of X to the 4th. Right, so same kind of thing that we just did. Nope, right away. All right, so something like this, exactly this same setup can be applied there. All right. Okay, so I'll let you to take a look at it. If you have questions with it, let me know. All right. So back to this, or before we leave this part, any questions with this? All right, then we're going to make a break into the part 2. And actually, I'm sorry, I lied to you. We have this last bit that I left. I said I was going to leave this for the end, because we're going to come into that. All right, so last little math fact for this gamma distribution. And that's what we're going to pick up within the part 2 stuff. So if I have, give myself some space here, a special case of the gamma distribution. Let's see here. I'll just write this out. So the gamma density is, what is it? 1 over beta to the alpha times gamma to the alpha x to the alpha minus 1 times e to the negative 1 over beta times x. So suppose I have this. Alpha is 1, beta is 2. I'll plug them in. So I have 1 over just 2, 2 to the 1, gamma of 1 times x to the 1 minus 1 times e to the minus 1 over 2 x. Right, just plugging in all my necessary numbers. 2 to the alpha, 2 to the 1 if we like. Okay? So let's see. 1 minus 1 is obviously 0, so that's a power of 0. So that goes away. Gamma of 1, right, would be 0 factorial, which is 1. So this really simplifies to 1 over 2 e to the minus 1 over 2 x.
Hold on, that looks familiar.
All right, and what does it look like? One over 2 e to the negative 1 over 2. Right, or 1/2 e to the negative 1/2 x. That's actually an exponential when lambda is equal to 1/2.
Or beta is equal to 2.
Or beta is equal to 2. Right? Because lambda times e to the negative lambda x is an exponential.
So this would hold
So-
for any value of beta, assuming alpha is 1, right?
Right. So beta was generic here. So the real math fact, I would have put that.
With an alpha of 1 is just an exponential distribution.
Correct. So if I have any gamma where alpha is equal to 1, is an exponential where the beta, right, is my, I wrote that backwards. I'm sorry.
Beta.
All right, sorry. Messing this all up. Where my lambda for my exponential is 1 over beta. That's what I'm going to write.
Beta is beta.
All right. Okay. Sorry about that. Okay, so with that, I'm sorry, I'm going to roll into this part 2